In the previous video, we discussed the evolution of artificial intelligence, machine learning and deep learning from a historical and scientific progression. One of the key questions that emerged from that foundational discussion was a simple yet profound one. Why did deep learning become so extraordinarily successful? Why were deep neural networks suddenly able to achieve massive breakthroughs in computer vision, natural language processing, speech recognition, and complex multimodal systems, outperforming traditional statistical models? The answer lies in a powerful defining paradigm known as representation learning. In this video, we will look under the hood to explore what representations actually are from a mathematical and geometric perspective, why the feature engineering bottleneck limited traditional machine learning, and how deep layers exploit compositionality to learn these features automatically, and the major open research questions surrounding representation learning today. To appreciate the paradigm shift of representation learning, we first need to understand the fundamental limitations that came before it. Consider a standard computer vision task, such as distinguishing between images of cats and dogs. Traditional machine learning algorithms like support vector machines, decision trees, or random forests are highly efficient mathematical classifiers. However, they struggle immensely when fed raw high-dimensional data such as grid of raw pixel values. This is largely due to what mathematicians call the curse of dimensionality. In exceptionally high-dimensional spaces, data points become isolated and sparse, making it incredibly difficult to find a meaningful decision boundary without human intervention. To make traditional algorithms work, researchers and engineers had to act as the interpreters. We had to spend months manually designing input features through intense feature engineering. For vision tasks, this meant handcrafting mathematical descriptors like edge detectors, color histograms, or texture descriptors. Similarly, in early natural language processing, practitioners manually designed features based on word frequencies, n-grams, or hard-coded syntactic patterns. Under this old paradigm, the success of an AI system did not depend on how smart the algorithm was. It depended entirely on the quality of these human-engineered features. This process required massive domain expertise, was prone to human bias, and simply could not scale as data sets grew exponentially. This drove researchers to ask a pivotal question. Instead of humans hand designing features, can a machine learn the underlying structure of the data completely on its own? Before we see how a network achieves this, let's define what a representation actually is. Formally, a representation is a way of transforming and encoding information so that it highlights meaningful structure, making a downstream task easier to solve. Take a digital image. To a computer, it is initially nothing more than a tensor of raw numerical pixel values. If you shift a single light source or rotate the camera by 5 degrees, every single pixel value changes completely, even though the object in the image remains exactly the same. Raw data, therefore, is highly sensitive to noise and lacks abstraction. The core challenge of modern AI is transforming that raw data into invariant representations that capture semantic meaning. Instead of looking at individual pixels, it is vastly more useful to represent the data in terms of its underlying latent factors. Lines, contours, geometric configurations, and object parts. For language, it means moving away from treating words as isolated symbolic strings and instead representing them according to their contextual semantic profiles. Automatically discovering these latent layers of meaning is precisely what we mean by representation learning. Mathematically, a natural neural network can be viewed as an information processing pipeline designed to continuously transform one representation into another. At each successive hidden layer, the input space is mathematically wrapped, projected, and refined through a series of linear matrix multiplications followed by nonlinear activation functions. The magic of deep learning is that this transformation happens hierarchically. During optimization, the network naturally organizes itself. The earliest layers, which are closest to the raw input, specialize in capturing highly localized, primitive visual structures. As we move deeper into the hidden architecture, the network automatically aggregates these low-level features into increasingly abstract, high-level semantic concepts. Think of an image recognition model. Layer 1. Layer 1 detects edges and special orientations. Layer 2 combines those edges to detect junctions, corners, and textures. Layer 3 aggregates those textures into semantic parts like eyes, ears, or wheels. The final layers integrate these components into a holistic representation of a complete object. The engineer does not write code telling layer 2 to look for a circle. The network discovers that circle is a useful intermediate representation entirely on its own through gradient descent. This ability to build abstraction layer by layer is a phenomenon known as hierarchical learning. Why does this work so remarkably well on real-world data? It works because it exploits a fundamental property of our universe, compositionality. The natural world is fundamentally hierarchical. Complex structures are composed of simpler components, which are in turn composed of even simpler primitives. Human language follows the exact same syntax. Letters compose words, words compose phrases, phrases compose sentences, and sentences compose abstract ideas. By mirroring this structural hierarchy, deep architectures can express an exponentially large number of variations in data using a fraction of the parameters that a flat shallow model would require. We see this exact same principle governing modern large language models. The early layers of transformer process basic token identities and local syntax, while the deeper attention blocks extract long-range dependencies, contextual nuances, and high-level semantic themes. In modern AI research, these layered representations are explicitly operationalized as embeddings. An embedding is a low-dimensional continuous vector space where the geometric distance between points is directly reflects their semantic relationship. When a network is fully optimized, objects, images, or words that share conceptual similarities are mapped to nearby coordinates within this latent space. Crucially, these spaces don't just cluster data, they capture complex linear semantic arithmetic. The geometric directions within the vector space correspond to meaningful real-world attributes such as tense, gender, or scale. Whether you are looking at vector databases or semantic search, recommendation engines mapping user preferences, or modern vision language models like click, CLIP aligning images with text, vector embeddings. Vector embeddings serve as the universal currency of modern artificial intelligence. By shifting the burden of feature extraction from human experts to data-driven optimization, representation learning fundamentally revolutionized the AI landscape. It broke the feature engineering bottleneck and unlocked dramatic leaps in performance. In computer vision, enabling real-time object detection and pixel-level segmentation. In natural language processing, powering massive foundation models capable of contextual reasoning. In multimodal systems, allowing architectures to map completely different modalities like audio, text, and video into a single unified latent space. And in scientific domains, allowing models to map the geometric structure of molecules, accelerating drug discovery and biological modeling. However, from a rigorous research perspective, representation learning is far from a solved problem. It remains one of the most active and vital areas of investigation in deep learning theory. As researchers, we are constantly dealing with critical open challenges. Interpretability. How can we reliably decode and audit these high-dimensional latent spaces to understand why a model behaves in a certain way? Sample efficiency. How can we design networks that learn robust representations from limited data, mimicking human-like sample efficiency? Out of distribution robustness. How do we prevent learned representations from shattering when exposed to minor distribution shifts or adversarial perturbations? Neurosymbolic integration. How can continuous vector representations be effectively combined with discrete symbolic logical reasoning? Answering these foundational questions is key to moving past mere pattern recognition and unlocking true generalized intelligence. To recap, in this video we explored how representation learning liberated AI from manual feature engineering, how deep neural networks leverage compositionality to build hierarchical abstractions, and how vector embeddings map the geometry of data. In our upcoming video, we will build directly upon this foundation by analyzing a massive architectural breakthrough that completely transformed how networks construct context attention mechanisms. Understanding attention will clarify exactly how transformers and modern foundation models dynamically reweight their representations on the fly. As I continue to document my research journey through this public portfolio, my core focus remains centered on the model robustness, representation, stability, and generalization. I am actively exploring opportunities to collaborate in research projects and participate in research opportunities. If you are a principal investigator, professor, or a researcher working on representation theory, geometric, deep learning, or multimodal systems, I would welcome the opportunity to connect. You can review my profile on the portals such as LinkedIn and GitHub, which I can send details on email. Thank you so much for your time today. If you found this research breakdown insightful, please consider subscribing, and I will see you in the next video. Thank you.